Hi. Because we cannot find a good time for everyone to attend, so I decided to record this material, and then so you can each watch it in your own time. So as TAs for this physics 30, 40, 50, even though the students are not required to know this material, but the TAs you should know, and this will help you in explaining the data analysis procedures to the students. And then especially if there are some more mathematically advanced students, then if they ask a question about this, then you should be able to answer. The question is about the basic ideas behind the least square fitting that you find in many computer softwares. So the idea is all embedded in this central limit theorem. And so I will go over this note that I have sent all of you. Okay, so the idea is the following. The idea is very simple. Let's say that for the city of Rhode Island, for the state of Rhode Island, they say, let's say we want to know the state for planning purposes. They wanted to know, say, men at age 56, my age, okay? Men at age 56, what is our weight distribution? Okay, so in other words, let's say there are, let's say 50,000 people my age, okay, men my age, there are 50,000 of us. So if you go count and then say this is 175 pounds, okay, and then this is like a 200 pounds, okay, this is like 150 pounds, okay, so forth. And then if you go count and they said, well, between 150, 155, you count how many people, and then the next 5-pound average, you count how many people, and then you count how many people, and so forth. Okay, so if you do if you count all 50,000 of us, then you will get this distribution. Okay, you'll get this curve. Okay, but to count all 50,000 is a very expensive undertaking, and the state of Rhode Island does not want to spend that money. Okay, so nevertheless, they want to know this number. Okay, so they don't care so much about the distribution, although they should, but as a matter of engaging the overall health of our group, is this mean value mu. Okay, the mean weight. Okay, this is 175 pounds. Okay, so if this value is more and then it's less healthy, if it's less, it's healthy. Okay, so nevertheless, let's say the state wants to know this value mu. Okay, and then so there's one way that you can get a measurement of this mean value by taking smaller number of measurement. Okay, so that's the value of the central limit theorem. The central limit theorem says that if I don't go take a measurement of 5,000, but let's say I'll go measurement of 10 people, okay? And then every time I take a measurement of 10, I get an average value of mean here, okay? So then what happens is if I take another random measurement of 10, so I initially take 10 measurement, and then I throw the samples back to the population, and I take another random sample of 10. Okay, then another value here, okay? And then I take another 10, okay? I take a few times, a few times. Then what I will find that what you find is that this value is going to be around this true mean value of the population, and then this small sample average will obey a normal distribution. Okay, so regardless of this original distribution is, this mean value will satisfy a normal distribution around the true mean. Okay, so this is enormously valuable because by doing a small number of measurements, let's say I do a sample of 10 and then I do 10 times. Okay, so if I just do 10 times, how many number of people I have counted? I only get it 10 to the, so I have 10, 10, 10, and then I do 10 times. So I would have a 10 to the 1 to have, oh, that's to, if I do 10, 10, 20, and then I will do 10, I will just do 100 times. Okay, so this is times 10, yes. Okay, so what I have is 100 times. 100 population. So what I did is I took measurement of, so I take a random sample of 10, I take another random sample of 10, another sample of 10, I do 10 times. So every time I have 10, I do 10 times, I multiply by 10, okay? So I have total counted the number of people, so only 100 people, okay? But then what I find is that my 10-time average, sorry, okay, so what I find is this 10 time 10 measurement, and when I bin them, and I will find that they will satisfy a normal distribution around the mean value mu here, okay? So let's see how this comes about. Okay, so this is the basic idea of the basic statement of central limit theorem, okay? So we define mu as the population mean, means I count everybody, okay? So it's a quantity that definitely exists if we measure the whole population, but we don't want to do that because it's too expensive, okay? So if I define xi, I is n independent samples. So that's, let's say I take 10 random samples from the population. So that means every sample I take is a random sample. So if I take the first person, and then I take the second person, and then, so my first person would be from this distribution, okay? I randomly take one of them, okay? My second one is also from here, from this sample, from this population, okay? So in other words, my x1 and the x2, okay, are independent samples from the population, but they all obey the same distribution. So they're identically distributed, okay? So what it means is this xi is a sample of random variables, each of which is what's called independent, identically distributed variables, the IID, okay? So IID is a very important concept in statistics, okay? What it says is that every sample I get, this xi, I get is from the population, and that each time I take a sample is independent of the next time, okay? So then, so of course, when you take 10 samples, there's a little caveat is when I take the sample 1, Bob, and number 2, Sean, number 3, David, and so forth. And then, so I don't put it, when I take X2, I don't put the X1 back into the population. But it's 50,000 minus 1. So it's a small negligible effect, okay? But when I take my second 10 samples, I actually put my first 10 back into the population, randomize it. So then my next 10 does include the previously counted people, okay? So why do I want to do that? Is because then I do not mess up my original distribution, okay? So I'm taking a small sample, each of which is a independent, identically distributed random variable, okay? So it's a draw from the same distribution. That's the key. Okay, I hope I'm clear on that. Okay, so then, so now I can first define what my population mean is. My population is, I count all 50,000 men in the state of Rhode Island. If I can do that, then there exists a true mean value, okay? The mean value would be just add up everybody's weight and divided by the total number, okay? I can also calculate the standard deviation. How do I do that? I take every person's weight minus the mean value, I square it, and then I add up all 50,000 of us and divide it by 50,000. So this is the mean square deviation, okay? Or if this is the position of a Brownian particle, then this would be the mean square displacement. Okay, so sometimes this is called the MSD for the general statement, the general purposes, okay? So now, so just keep in mind that mu is the population mean, is the true mean value, okay? And the sigma square is the mean square displacement, okay? The square root of this is the root mean square, okay? So RMS. Now, if we take a small sample of size n is 10 from the population, then the sample mean is just add of all 10 and divided by 10. So this is the sample mean, okay? Of course, when I take a small sample mean, the chances are it's gonna be different from the true mean by an amount that is the difference. Okay, so I take the mean of the sample minus the population mean, and there's going to be a difference, okay? So I call this mu as a true value, okay? Is the population mean. And then so xn bar is the sample mean, okay? So the whole idea is we are trying to find a way to take a small measurement that can give us a statement about the true value mean. Sometimes you absolutely cannot get this mu value because this population, and it's not 50,000, it can be 5 billion, okay? Then you absolutely cannot take a measurement of a whole billion people, okay? So then in that case, this becomes an absolute necessity to use statistics to get a good measurement of mu, okay? Okay, so this is the difference between the sample mean and the population mean. Okay, so now the rest, the next few lines is just algebra. Okay, so I rewrite this mu with this n mu divided by n. So I did nothing but putting a 1 here, okay? So by doing that, what I can do is there are n terms of mu, I can redistribute this n terms to each of these n terms, okay? So x1, the first sample, Bob, okay, minus mu. The second one is Sean minus the mu, and so forth, okay? So you get this, okay? So you'll get n terms, okay? This n term is the individual sample, individual IID minus the true value, okay, individual IIDs minus true value, there are n of them, each divided by n, okay? So the sum of this gives me the original, the sample mean minus the true mean, okay? So now there's if I square this, term, then what I get is, this is just from the algebra, so a plus b plus c plus d and so forth. If I square it, I get a squared plus b squared plus c squared plus d squared, and then plus bunch of cross terms, okay? So then what happens is, we notice that because these terms are square, means these terms are always positive, okay? So, but the cross terms gonna have all kind of different signs, because x1, Bob can be lighter than the mean, Sean can be heavier than the mean, and so forth. So then the cross term, so for example, there's a term is x1 minus mu divided by times x2 minus mu times n. So this cross term is going to be negative, because one term is positive, is negative, the other term is positive, okay? So what you're going to get is a loss of cross terms with different either positive or negatives, okay? So then the idea is, I take this, I don't take this just one time of 10, I take many, say 10 times of this measurement. Then I do an average of this guy here. Okay, so I take an average of this guy. Okay, so what it means is, I take a n times of a small n times of this guy. So then what I'm gonna get, the average is, I'm gonna average this n times of this square terms, and I'm gonna sum and then divide it by the n. Okay, so then what I get is this. Then what I get is that I'm going to average, because this guy is a constant, so this average, so I should emphasize that this average means I take, so this I take a measurement of some quantity an, okay? So I take a measurement of n times, and then divide it by n, okay? So this bracket means this, okay? Means this. So this, if I take a bracket on this guy here, then I take a bracket on, sorry, on all of this. Okay, but because this guy's a constant, I take it out of this. So I should call this one n prime. Okay, so to make a distinction from this n here. Okay, so then what I have is, I'm going to average these guys, but because this guy's always positive, so this average is going to be positive, all going to be positive. But the cross terms are going to be averaged out to 0, because I keep on adding the quantities that are changing signs. Okay, so if I do many times, this term is going to be averaged out. Okay, so last time, and then Yusra asked, say, how many times you have to do average to make this cross terms go away? So honestly speaking, is infinite. So this is a little caveat of the argument, that in order for us to average out this this cross term to 0, we actually have to do many times, and strictly speaking, infinite number of times. Okay, so then what we get is that we only get the positive terms, the square terms, and then when you add them together, what you get is this quantity. In other words, this the difference between the sample mean with the population mean square, the average of the quantity, okay, is the average of the mean square displacement, okay, is related to the true to the mean square displacement of the population by square root of n. Okay, so which means is that if you take a a sample of n, if you take a sample of n, and then what you find is that your mean, so this is the definition I should emphasize, okay? So this quantity is gonna be smaller than the, sometimes this is called the variance, okay? Or sometimes called it the RMS, root mean square, okay? And so this this RMS is going to be smaller by the amount by the square root of n. So which means the bigger sample you take, the smaller the error is going to be. You will see that this quantity will go into the Gaussian distribution later. Okay, so this quantity has significant value to us. Okay. All right, so at this point, if you're a little confused, I encourage you to stop the video and then rewind it, go back, and then to rewatch at the beginning of how the sigma is defined and mu is defined, and what is the population mean, what's the sample mean, and so forth. Okay, so if you get it to this point, then we can continue. Okay, so now let's divide this quantity by sigma n. Okay, so this quantity, remember this quantity here depends on each individual sample, but this quantity here is the averaged quantity. Okay, so to make sure. So this quantity sigma n is not sigma n bar minus mu, rather is the square root of the averaged value of this quantity, okay? And so we define that, and then we will find that because this sigma n is sigma divided by square root of n, so I put the sigma here, and the square root n goes to the top, okay? So this is just algebra. I'm gonna call this new quantity a new random variable, yn. Okay, so this yn is a new random variable, and we'll see the value of this, okay, very soon. Okay, so we remember that this xn is just xn1 plus x2 plus xn, right? And then this mu I can rewrite as n mu over n, and then I can rewrite it as this, okay? And then I cancel out this n and the square root n. Okay, so then I have a square root n downstairs. So what do I have? This yn, this new random variable, is 10. So if I take a sample of 10 small samples, then I have 10 terms here. Okay, so depends on whatever the small sample that we take. And whatever we take, if we have 10, there's 10 terms. If we take 100, then there's 100 terms. Okay. So this new random variable has the number of terms that's dependent on the size we choose. Then we notice that if I square this guy, I'm going to have the same trick that I have a bunch of square terms and plus cross terms. But because I take an average, then I'm going to average out the cross terms, okay? And then, so what you find is then if I do that, I find that this average is just equal to 1. So what this yn is just a normalized xn minus mu, the sample mean minus the true mean value. Why do we want to do that? For mathematical convenience, that comes next. Okay, so now we wanted to develop the mathematics to analyze the this yn. Okay, just keep in mind that what this yn is this. Okay, so this is a definition. Okay, so now we want to develop the mathematics to describe the distribution of the sample mean around the true mean. Okay, so let's first develop the math. Okay, so if x1 and x2 are independent random variables with their own distributions. Okay, so let's say the x1 is drawn from a distribution of px1. Okay, x2 is from px2. Okay, uh, uh, so this mathematics is broader than what we have at hand. Okay, so we are drawing the random variables from the same population, so therefore these p's are the same distribution, but the math that we are about to develop is can be broader. In other words, x1 can be from one population, one distribution. So I can imagine so this um, so we can imagine that we can draw the first sample from the population in Rhode Island, okay? And then I draw the second random population from people from California, men at the age 56. So obviously, probably true that the Californians, because they are sunny every day, people exercise more than we do in New England. So people in California are healthier. So I can imagine that the Californian weight is something like something like this, around, let's say, maybe it's 150 pounds. Okay, okay. So let's say is something like this, some distribution like that. And the Rhode Islanders are more like this. Okay, more like 175, and then skewed more towards more heavyweight people like me. Okay, so this would be px. This would be px1 Rhode Islanders, and then this would be px2 Californians. Okay. Okay. So this would be what I call the x1 population. This is x2 population. Okay. So the idea is if we x1